Today, we're going to create a tessellation and displacement shader in both Unreal and Unity. Let's go. Before we get started, it's important to understand what tessellation and displacement are and why we would want to use them. Tessellation and displacement are a dynamic way to add detail to your mesh without needing to store a highly detailed mesh in memory. The brute force method for doing this would be to detail your mesh in ZBrush or other sculpting software, and then bring the base mesh into the engine with millions of triangles. This would make a mesh that's really expensive to load into memory and really expensive to render. Instead of doing that, we can create a regular low poly model and a height map that indicates where additional geometry should be displaced. And then in the shader, we can tell the graphics hardware to subdivide our mesh into millions of triangles. But the difference is, because we're doing the effect in real time, we can create the additional detail only where we specifically need it for every frame. So we can dynamically add detail where it's needed and leave it out where it's not visible. So tessellation means adding triangles to the model by subdividing it, and displacement means moving those extra triangles around so they can make the shape of the model more complex than it was originally. This technique works really well on organic models that use mostly uniform size triangles. So with that explanation out of the way, let's jump right in and create our shader in Unity. So here we have a brand new material in the HDRP pipeline. And the first thing that we need to do in our new material is come over here in the Graph Inspector and select the Graph Settings tab. Now we're going to come down here to Tessellation, and we're going to turn this box on. And when we do, what that's going to do is it's going to expose two new items in our master stack in the vertex section here called Tessellation Factor and Tessellation Displacement. So the first thing that we're going to focus on is Tessellation Factor. And what that means is how many new triangles we're creating in our mesh. So for now, we're just using this simple sphere mesh here. And if I switch over to wireframe view, you can see that our sphere mesh is relatively low poly. I just have a fairly small set of vertices here. And what we're going to do is increase our tessellation factor and see what happens when we do. All right, so when I set the tessellation factor to 2, now you can see that our low poly sphere is a little bit higher poly, but probably not quite high enough polygon count to actually do some good displacement. So let's turn it up a little bit more. Let's just set it to a value of 32 for now and see what that does. Now you can see we've got a few extra triangles going on here. So this is pretty cool. We've got a really densely detailed mesh. Obviously, if we switch to shaded mode, you really can't tell the difference between that and the model that we had before. But if we look at it in wireframe, wow, that is a lot of triangles going on right there. Okay, so we've set our tessellation factor to 32. And now we need to do displacement. So for tessellation displacement, this is basically you specifying the offset of each of the individual vertices and where they're going to go. So let's start out just by taking the normal vector node. And what this is going to do is it's going to tell the model, hey, I want to offset each of my vertices along the normal. So let's just plug this into our tessellation displacement and see what happens. So I'll hit save, and our sphere is gone. But if we zoom out a little bit, you can see that our sphere is just a little bit larger. So what happens is our normal is unit length, which means it's a unit of 1 or 1 meter. And so our vertices have all been displaced outward along the normals of the mesh 1 additional meter. if I want to control how much displacement is taking place, what I can do is multiply our normal vector by a value. And this value I can use to control the amount of displacement that we're applying. So I'm just going to give this a value of 0.1. So we're now displacing the mesh 1/10 of a meter along the normals. And so now you can see that my sphere is not quite so large. It's a little bit smaller, but if I just if I set my multiply to 1 or to 0 rather, this is going to give me no displacement and my sphere is going to be back to the original size. Well, this is not really that interesting because all of my vertices are being displaced uniformly. And what I really want to do is use a texture to make some vertices displaced more than others. And so I'm going to open up my Create Node menu here and do a search for Sample. And I want to sample a texture, but if I use a Sample Texture 2D, that node doesn't work in the vertex shader. I need to use Sample Texture 2D LOD. There are some features that Sample Texture 2D uses that only work in the pixel shader. And so I need to use Sample Texture 2D LOD because it doesn't use those features. All right, so I'm gonna click here on the picker and I'm gonna pick a height map. I'm gonna pick my cobblestones height map here. You can see this texture is 256 by 256. It's 85.4 kilobytes, pretty small. I don't need very high resolution in this map because it's just displacing vertices. It's not doing its operations per pixel, and so I can get away with a fairly low resolution texture here. All right, so I have my normal vector and I have my multiply here that's controlling how far I want to displace things. Let's just set this to 0.04. And now we're going to multiply by our height map. So I'm going to add another multiply in here. And for this multiply, we're going to wire in our height map. And before we do that, actually, I want to take a look at what this texture actually looks like so you can get an idea for what it's going to do. So let's just wire it into base color. And let's see what that does. Okay, so you can see that I have these cobblestones that are white where the displacement should be high, and it's kind of black where the displacement should be low. So that works pretty well, although there is a little bit of stretching going on. And so I want to modify the UVs just a little bit. I'm going to add our UV node to bring in my UV coordinates. And then I'm going to multiply my UVs by 4 and 2 just to tile this a little bit more. So let's plug these UVs into my texture and take a look at our result from that. Okay, now you can see that our cobblestones are a little bit more uniform shape. This is not something that you necessarily have to do, but it looks just a little better if I do this for demonstration purposes. So this is what our cobblestones are going to look like. And let's wire our height map here into our multiply, and then wire the result of that into our tessellation displacement, and take a look at what we're going to get now. Wow, cool. So you can see that our cobblestones are bumping out of the surface. It's especially noticeable here on the silhouette, and not quite so noticeable here when we're looking straight at the sphere, but especially on the angles where the cobblestones overlap each other. It's really apparent, and it adds a ton of realism to our model. It makes those cobblestones just really pop out of the surface. Okay, so right now we're using our height map to shade our model, and that's a little bit unrealistic, so I'm going to delete this connection so that our height map is no longer being used for color. But one thing that you'll notice when we do that is that our normals no longer look correct, because we're bumping out the vertices on the surface of the model, but we're not changing the normals at all. So in order to fix that, that's really simple. It's something that we do all the time. We just need to add a standard normal map. So I happen to have a normal map already that is the same shape as my height map. It's this cobblestone's normal map here. So I can just grab this one, and then I can plug this into my normal map socket, just like we do very commonly. And then if I hit save here, oh, I need to use the same UVs here. Now this is something interesting that I want you to notice. I have my UV coordinates here, and I'm multiplying them and then passing them into the sampler that's sampling my height map. But if I try to take those same UV coordinates and drag them down here to my normal map, you notice that these sockets kind of close themselves off and say, hey, you can't connect to me. And the reason for that is because this data is going into our vertex shader, but this data is going into our fragment or our pixel shader. And so what I need to do is just duplicate these nodes here. And now I can use the same nodes, but just a copy of them in order to sample my texture in my fragment shader. And that's because you can't take data from the vertex shader and just use it in the fragment shader like that. You need to do some special things in order to pass data back and forth. So we're going to keep what's going on in our vertex shader separate from what's happening in our pixel or our fragment shader. All right, let's take a look at what we've got now. Oh, and there's one thing that I forgot. We need to set the type on our texture sampler to a normal map so that it knows to do the special calculations required for a normal map. Okay, and there you go. Now we have our cobblestones and they're bumping out. We're doing tessellation and displacement. And if we take a look at our wireframe, holy cow, do we ever have a ton of triangles. We can zoom in here and you can see, wow, we've got triangles to the moon. Okay, this is not specific. This is not especially optimized. And if you were to put a mesh like this into a game, you would just totally destroy your frame rate. Now, the cool thing about tessellation is that we can actually control where these triangles are getting added and how. The first way to control how they're getting added is based on the distance from the camera. And this is something that happens automatically. Let's switch back to wireframe, and we're going to zoom out here. And what I want you to notice is that as we pull further away, the triangle count is actually reduced. And right now it's so high that maybe you can't even tell. But as we're moving further away, actually, let me dial this back just a little bit so that maybe it's a little more obvious. So right now we have our tessellation factor of 32, but I'm just going to set it for 8 for a minute so that you can see the triangle count reduce as we move away. Yeah, that's a little more obvious there. So when we're zoomed in, we get our full tessellation factor, but then as we move farther away, it's reducing the amount of tessellation. So now when we're at this size, we're back to basically the same triangle count that we were at the beginning. But then as we zoom in, it's adding more and more triangles for us. So the game engine is optimizing our tessellation so that we only need exactly the number of triangles that we're using and not any more. And if we go over to our graph settings on our graph inspector, you can tweak these settings over here as subsettings under tessellation to control how that distance-based tessellation works. I'm not going to go into the details of that right now, but you're welcome to take a look at the documentation and play around with these to see how that works. So we can control the number of triangles that we have based on the distance of the camera to the model, and optimize our tessellation that way. Now, the other thing that we can do is if we take a look here, and this is something that I mentioned before, we don't see the tessellation very much when we're looking straight at our model. We mostly see it around the silhouette edges. And so what we can do is, instead of just setting a hard-coded value here for our tessellation factor, we can actually control the tessellation factor based on whether or not the surface is facing toward the camera or perpendicular to the camera. So we can do some optimization of our tessellation based on the angle to the camera. So let's do that next. So the first thing that we need to add in order to create this optimization is a normal vector. So I'm going to add a normal vector. And now we need to do a dot product between our normal vector and our view direction. So I'm going to add a dot product node. And now we need our view direction node. And so what this is going to do is tell us what the relationship is between these two vectors. It's going to return a 1 if the vectors are parallel to each other, and it's going to return a 0 if they're perpendicular to each other, which basically tells us, are we facing the edge or not? So just to get a better idea of what this is looking like before we plug it in, I'm going to get rid of our normal and our tessellation, and let's just plug this value here into our color for now so that we can get feedback on what that's looking like. Okay, it's a little bit hard to see because of the lighting, but you can see here that we're getting white here where the surface of the model is facing the camera, and we're getting black on the edges where it's facing away from the camera. And that's exactly what we want, but we want it actually inverted. So I'm going to add a 1- node. And what the 1- does is it subtracts the result from 1, and it's basically inverting these results. So if we plug this in and save it, now you can see we've got this black dot where the surface normals are pointing straight at the camera. And then as the normals go more perpendicular to the camera, we get kind of a white halo around the edge. And that's what we want, because we want to do our tessellation here on the silhouette and not do it here in the middle. Now we can adjust this a little bit if we add a power node. So we raise this to a power of, say, like 1.5. And what that will do, if I just have a power set to 1, you can see here in the preview, it looks very similar to this. If I just have the power set to 1, I have the black dot that's kind of small. But if I want to optimize it even further and push the black out toward the edge, I can raise this to like a power of 2 or 3 or 4. This might be a little bit too much, and so what I'm going to do is go with the value of 1.5. And this is something that you can tweak depending on how optimized you want to make the effect. All right, let's take this power node and multiply it by our tessellation factor. So we have our tessellation factor set to 32. And so what this is going to do is we have our mask here that falls off on the edges. And so by multiplying it by 32, we're going to get a tessellation factor of 32 on the silhouette edge, and then it's going to get smaller as we come in here toward the middle. So let's plug this into our tessellation factor. Well, actually, first, let's take a look at our wireframe here. You can see we still got triangles to the moon. But if I plug this into our tessellation factor, what it's going to do is tessellate the model pretty heavily on the edges. But now in the middle, you can see that I'm not very tessellated at all. And this is what we're going for. This is an optimization so that we're putting triangles where we need them on the silhouette edge, but not here in the middle. This is the real power of tessellation because it gives us detail where we need it when we're up close to the model and on the edges where it's most visible. And we can tell our shader, hey, I don't need triangles when I'm looking straight at the model. We don't need tessellation there. So let's remove it from that. And I also don't need triangles when I'm further away from the model. So go ahead and automatically remove the triangles as I get further away. That's the real power of tessellation. If I were to bring in a 1,000,000 poly model, I wouldn't be able to do that automatically, but with tessellation I can. So now let's plug our displacement back in, and let's plug our normal map back in. And I'm just going to disconnect this from the base color and maybe make the base color a little bit darker. And I'm going to make the smoothness a little bit higher. And this is just so that we can see the results a little bit better. Okay, so now you can see in the wireframe that I'm getting really nice tessellation here around the edges. And in the middle, I'm not using triangles where I don't need them as much. So if we switch to shaded view, cool. Now we've got our sphere with tessellated geometry shapes, and you can especially see them around the outsides. And it still looks the same here in the middle, but I'm not actually spending those triangles. If we look at wireframe again, it's not tessellating our sphere here in the middle where triangles aren't needed. Now, as I rotate this around here, you can see things moving a little bit, kind of undulating. And that's where tessellation is being applied or taken away based on if the model is facing the camera or not. And so that's where you need to adjust this power value and also adjust this overall tessellation value. So these are two parameters that you might want to expose to the material as exposed tweakable parameters so that the artist can choose these. Now you want to be careful with this one. You want to try to take the overall tessellation factor, the maximum tessellation factor, only as high as you need it. You might be able to get away with something as low as 8. But if you're not getting enough, surface shape, you can turn this up. So this one is going to give you quality versus performance trade-off. And the same here. If you set this to a power of 1, you'll get fewer of those little bubbly lines, but you'll end up with more triangles. If we switch over to wireframe view here, we have more triangles here. The higher this power value is, the further toward the edges it's pushing the tessellation. If I were to set this to a power of 5, I would only be getting tessellation on the very edge. But then if we take a look at shaded mode, you can see there's some fairly harsh bubbling artifacts here where our tessellation kicks in around the edges. So in my case, it's working really well to set this power to 1.5. And then our tessellation factor to 32. But like I said, these are values that you need to tweak per model to make sure that you get the right trade-off between quality visuals and performance. Okay, so that's how tessellation works. We are controlling how much tessellation to apply based on the angle of the surface here. We're controlling how much displacement to apply based on our height map here. That is getting multiplied by our normal vectors. Oh, and then we have this multiply value here. This value is defining our maximum amount of tessellation. So if I were to turn this up to something like 0.1, say, now I'm going to get a ton of tessellation. That's probably a little too much. The lower this number is, the less of these like bubbly artifacts that you'll see. But the less tessellation you'll get as well. So this is going to be a trade-off here. For my cobblestones, a value of 0.04 works really well. All right, and then we just use a standard normal map to create the normals of the mesh. And we end up with a really realistic looking effect. Cool, well let's switch over to Unreal and I'll show you how to do the same thing there. Okay, here we are in Unreal, and the really big thing to understand about Unreal is that Unreal 5 does not have tessellation. And I'm not sure why that is. I think maybe Epic wants to encourage everybody to use Nanite instead. And so Unreal 4 has tessellation, but Unreal 5 does not. And so in order to do this demo, I've switched back to, in the series we've been using Unreal 5, but in order to do the tessellation demo, I've switched back to Unreal 4.27. So the first thing that we need to do in Unreal is we need to come down here to our settings of our material and find the tessellation settings. And these settings, again, do not exist in Unreal 5, so we're doing this in Unreal 4 instead. So by default, this is set to no tessellation, and I'm just going to set this to either flat tessellation or PN triangles. Let's go with flat tessellation for now. And what that does is it enables us to use world displacement and also tessellation multiplier. Now here's the next thing that's interesting about Unreal. The overall tessellation factor that we're using is something that's hard-coded into the engine. In Unity, we were able to set that value, and we set it to a value of 32. But that value is hard-coded, and there is a place in code where you can change it if you need to, but it's really not intended to be changed. And so this tessellation multiplier value here is really just intended to be between 0 and 1 as a multiplier for the internal value that's set inside the engine. And so what we're doing here, instead of specifying that value of 32 like we did before, we're just looking for a value that's between a range of 0 and 1. And so just like we did in Unity, what I've got here is a dot product between my vertex normal and my view vector. So I'm creating a view vector with the camera position node and the absolute world node. I just subtract the absolute world position from the camera position and normalize. This gives me my view vector. Then I do a dot product between the vertex normal and my view vector. And then I do a 1 minus x, which is flipping it or inverting it. And let's just disconnect all of these for now and just plug this into my base color node so that you can see what I'm getting. If I switch this to unlit, you can see that this is the same mask that I was using in Unity, where I'm getting a dark here in the middle, and then as I go toward the edge, my value gets brighter. And so what this is doing is it's making it so that my tessellation factor along the edge is going to, or my tessellation multiplier rather, is going to be 1 along the edge, and then as we come in here facing more toward the camera, my value is dropping down. So let's see, here I've got my power set to 2. Let's drop this down to 1.5, and you can see with that value, I get a little bit less fall off. Okay, so if I disconnect that there, and then set this to wireframe, what you can see now is that I've got tessellation around the edges and no tessellation here in the middle. But if I disconnect this, now I have uniform tessellation everywhere. And that's fairly expensive, which is why we're going with this optimization to just put the tessellation around the edges where it's most important. Okay, the next thing that I have is, this is my height map here. If I do a little preview, you can see I'm using that same cobblestones height map as I did in Unity. And I've got my texture coordinates here multiplied by 4 and 2, mostly just to make it look a little bit nicer on the sphere. And then I'm multiplying my height map here by my vertex normals, and my vertex normals are multiplied by 16, because the units of offset in Unreal are different from Unity. In Unity, a unit is 1 meter, but in Unreal, it's 100 centimeters. And so this is actually a very short surface normal. It's just 1 centimeter. And so I need to multiply it by 16 to get some decent bumps. So let's plug this into our world displacement. And now you can see that right along the silhouette edge, my bump map is bumping out. If instead of connecting this to the displacement, I connect it to the color, and then we switch to unlit here, you can see some interesting directions. This is actually showing me the world space directions where I'm pushing my vertices. What I actually intended to do was to plug my bump map in so that you can see what the bumps are doing. So where the map is white, it's bumping out, and where the map is black, it's not bumping out. So I'll wire this into world displacement. And then, just like we did in Unity, I've also got my, my cobblestones normal map, which I can connect to my normal socket. And so with everything hooked up, my normal map plugged in, my displacement map plugged in, and my tessellation multiplier plugged in, I'm getting some cool looking tessellation. And as I zoom away, the tessellation is reduced. If we look at it in wireframe again, you see as I get further away, there's less tessellation. And then as I zoom in, I get more tessellation, but only around the edges where it's important, where it's needed. All right, cool. So that is tessellation and displacement. I want to subdivide my model, but only in the specific areas where it's going to be needed. And then I want to use a height map or a bump map to displace the triangles of my model in areas where I want more detail. Now, you can use sculpting software like ZBrush, for example, and export your mesh on the lowest subdivision level, and then have ZBrush calculate the difference between your lowest level and your highest, so you can crank it up to like 7 subdivisions and put all kinds of extra detail in there that doesn't exist at the lowest level. And then you can tell ZBrush to calculate the difference between the two and output a displacement map for you. Then you can use that displacement map here to get all kinds of cool extra dynamic detail that you wouldn't be able to get otherwise. So that's kind of how that workflow works. And I'll put some links down in the description for other tutorials that show how to create content that way. Anyway, I hope you've enjoyed the video and that you're inspired to go out and create some tessellation and displacement models yourself, now that you understand a little bit better how to set up a shader that does it. Well, that about wraps it up for this week. Have a great week, everybody, and be sure to come back again for more shader goodness next time.